So today we'll learn about Friedel-Crafts alkylation. So first of all, what is this Friedel-Crafts alkylation? An alkyl halide, when it is treated with Lewis acid, it results in the formation of a carbocation which is later attacked by an aromatic ring. This is called as Friedel-Crafts alkylation. So first of all, we'll see the mechanism. In this, Lewis acid is nothing but a chemical species which accepts a pair of electrons. In this Friedel-Crafts alkylation, we will be taking AlCl3 as the Lewis acid. Now first we will take an alkyl halide CH3C, CH3H and Cl. This is a secondary alkyl halide which is treated with Lewis acid AlCl3. So what happens here? The lone pair of chlorine, it transfers its lone pair into the vacant p orbital of aluminium, and what happens after that? Chlorine gets a positive charge, aluminium gets a negative charge. As chlorine is positively charged, it will take the bond from carbon, leaving this carbon positively charged, and hence a carbocation is formed. This is the activated carbocation or activated electrophile. Okay, plus AlCl4 minus. Here AlCl4 minus is a better leaving group than Cl minus. Hence we have taken Lewis acid in this reaction, which is AlCl3. So this is the first step in the mechanism, which is activation of electrophile with Lewis acid AlCl3. Okay. Now after this first step, we have to remember two main points. What is the first point? In case of secondary alkyl halide or tertiary alkyl halide, full dissociation to form carbocation occurs. What does this mean? When we take a secondary alkyl halide or tertiary alkyl halide in the reactant, it will be dissociated completely into a carbocation only when we take secondary alkyl halide or tertiary alkyl halide in the reactants. But in case of primary alkyl halide, full dissociation to form carbocation can be denoted as C plus. Okay, carbocation does not occur. What does this mean? When we take a primary alkyl halide CH3 CH2 Cl, this is a primary alkyl halide which when treated with Lewis acid AlCl3, we will get a structure like this. This is negatively charged, this is positively charged, and carbon here is partially positive. Here this is the activated electrophile. This will be the final product here. When we take primary alkyl halide, we will not get a carbocation like this when we take a primary alkyl halide. So This is the first point in this, which we have to remember. So what is the second point which we have to remember? That carbocation rearrangements can occur if there is a possibility of formation of more stable carbocation. So what is this? If we take primary carbocation, or else if we take primary alkyl halide, what did we learn in the first point? That if at all we take a primary alkyl halide, it will not dissociate to form a carbocation. But if there is a possibility of formation of secondary carbocation or tertiary carbocation, then we can take primary alkyl halide, we can convert it into primary carbocation, then we can rearrange. There will undergo hydride shift and will form a more stable secondary carbocation or tertiary carbocation. We will see this through an example. First, let us take a primary alkyl halide, CH3CH2CH2Cl. This is a primary alkyl halide. Now this is treated with the Lewis acid AlCl3. What will be the product? CH3CH2CH2. This carbon will get a positive charge. Why does it get a positive charge? Because Cl will first form a bond with aluminium here, and aluminium gets a negative charge, chlorine gets a positive charge. As chlorine is positively charged, it will take the bond from carbon, leaving this carbon positively charged. So here we will be forming the primary carbocation C. Primary carbocation is formed. Now what happens? This will undergo 1,2 hydride shift. This is the first carbon, this is the second carbon. So this hydrogen, see, we can write this structure in this form, CHH. CH2 we have written in open form, and this is CH2 plus. Now this hydrogen will take the bond from carbon, will come out as hydride ion and will attack the positively charged carbon and will give us secondary carbocation. This is secondary carbocation. So the secondary carbocation is more stable than primary carbocation. Now to explain how to change this primary carbocation into tertiary carbocation, again we'll take one primary alkyl halide. Now again we'll take a primary alkyl halide, same CH3CH2CH2Cl. It is treated with AlCl3. Chlorine will form bond with aluminium. Aluminium gets negative charge, chlorine gets a positive charge. Chlorine will take the bond from carbon and will leave as AlCl4 minus. Carbon will get a positive charge. We have formed the primary carbocation here. Now what? Okay. So to form a tertiary carbocation, we have to add one more methyl group here. Okay. Yes. Now this is a primary carbocation. This can be written as CH3CH2 plus. Now again we'll see 1,2 hydride shift here. This is the first carbon, this is the second carbon. Hydrogen will take the bond from carbon, will leave as hydride ion. This hydride ion will attack the positively charged carbon center and will give us the tertiary carbocation. This tertiary carbocation is more stable than the primary carbocation. So what does this infer? That tertiary carbocations are more stable than secondary carbocations. Secondary carbocations are more stable than primary carbocations, which are more stable than the methyl ions. Okay. Only when you have a possibility of rearranging a primary alkyl halide into a secondary carbocation or tertiary carbocation, then only you have to take a primary alkyl halide, or else you have to go with secondary or tertiary alkyl halides in Friedel-Crafts alkylation. So we have seen the first step of the mechanism, which is the activation of electrophile with Lewis acid. Now we will go into the second step of mechanism, which is a rate determining step, also a slow step, which is the attack by benzene on this activated electrophile. Okay. In the first step, what we have seen, activation of electrophile with Lewis acid, where we have formed a secondary carbocation, which was this K plus AlCl4 minus. These were the products. Okay. These are the reactants. Now the second step is the attack by aromatic ring on activated electrophile. Okay, so this one is the activated electrophile. Aromatic ring here is benzene, which reacts with the activated electrophile CH3 CH3H plus. So what happens here? Let us take this carbon as first one and this as the second carbon. The double bond here is taken by the second carbon and will give us a negative charge on the second carbon and a positive charge on the first carbon. And then this negatively charged carbon will attack this carbocation and will give us a structure like this. Okay, this negatively charged carbon attack the positively charged carbon, giving us a structure like this. Here we have one more hydrogen, right? So in benzene we know that we have 6 hydrogens. Okay, so this hydrogen, the bond between the carbon and hydrogen is shifted between carbon and carbon, forming a double bond, and this hydrogen leaves the molecule, leaves this compound as H plus, and it will form bond with the chlorine from AlCl4 minus, which will give us the final products as, so final products are, see, benzene will form a double bond. Okay, the H plus, which was released from here, will form a bond with the chlorine in AlCl4 minus, which will give HCl, and last AlCl3. So here we can see the attachment of an alkyl group to the benzene ring. This is called as Friedel-Crafts alkylation.